Hello, in this video we'll be talking more about section 2.2, Systems of Linear Equations in 3 Variables. Here we will see and look at problem number 5, which is x plus y equals 0, x plus z equals 1, and 2x plus y plus z equals 2. First off, I'm going to rewrite a couple of these equations because they're not in the traditional form. I will rewrite that first equation as x plus y, plus, because there is no z term, I'll write that as plus 0z equals 0. Same thing for the second equation. I'll write that as x, because there's no y term, I'll say plus 0y plus z equals 1. And the third equation is just fine. I'll also label these as equation 1, 2, and 3. My goal will be, as usual, to take two of these equations to eliminate one variable, then another two equations to eliminate the same variable, and then combine from there. So, let's go ahead and do that. I'm going to elect to do equation 1 and equation 3. The reason for that is because they both have a positive y in them, so all I will need to do is subtract those. I will take equation 3 specifically, and I'm going to subtract away equation 1. So what that will look like here is 2x plus y plus z equal to 2. And I will subtract away equation 1, which is x plus y plus 0z equals 0. That will give me 2x minus x will just give me a positive x. Y minus y will give me 0. And z minus 0z will just give me a plus z. And that'll equal 2 minus 0 is 2. I will label this as equation 4. Now you may notice that equation 4 and equation 2 already have the same two variables in it, so I do not need to combine another two equations to create a fifth one. I should just be able to use equations 2 and equation 4. You'll also notice that they have the same variables in them. They both have x and z, and they both have the same coefficient specifically. So combining them is going to create something a little bit special that we haven't seen before. Let's say I take equation 4, our new one here, and I'm going to, again, subtract another equation. I'll subtract equation 2 from it. Equation 4 is x plus z equal to 2. Because I am subtracting equation 2 where I don't need the y term, I'll elect to use the original version of it. So I will subtract x plus z equal to 1. And this is going to make something special. I'll get x minus x, which is 0, z minus z, which is also 0, meaning I get a total of 0 on the left side there. But on the right side, I get 2 minus 1, which is 1. This should seem illogical, 0 equal to 1. It is a contradiction. 0 does not equal 1. Therefore, this system is what we would sometimes call inconsistent, which more importantly means that there is no solution here. When trying to solve for any place where all three of these equations are consistent, where they have a consistent set of solutions or individual solution, we get a contradiction, which means that there is nothing here. So I'm done with this problem. This equation has no solution. Let's look at problem 6 then. Problem 6 gives us another set of equations. We have y plus z equal to 1, which I will go ahead and rewrite that as 0x plus y plus z equal to 1. I also have x plus y plus z equal to 1, and x plus 2y plus 2z equal to 2. I'll label these equations as usual as equation 1, 2, and 3, and my goal is to try to combine these together to solve for x, y, and z. You'll notice that the first equation has both y and z with a coefficient of 1, and the second equation also has y and z both with a coefficient of 1. Meaning I should be able to just combine those two together and not get an equation of two variables. I actually should be able to eliminate both y and z. So let's do that. I'm going to take equation 2 and I'm going to subtract away equation 1. So that will look like x plus y plus z equal to 1. and I'm going to subtract away 0x plus y plus z equal to 1. If I do that, x minus 0x is just x, y minus y is 0, z minus z is 0, and on the other side I get 1 minus 1, which is also 0, which means I have my first solution here, x equal to 0. Using that, I should be able to plug that into some of our equations and start to continue forward from here. You're going to notice something special though, no matter what equation you elect to put x equals 0 into. And let me demonstrate this. Let's say I choose to put x equals 0 in equation 2. Let's see what that would look like. If I do that, I'm going to get 0 plus y plus z equal to 1, or just y plus z equal to 1. If I elect to put x equals 0 into equation 3, on the other hand, I'm going to get, again, 0 plus 2y plus 2z equal to 2, or just 2y plus 2z equal to 2. Or if I divide everything by 2, because they do have that same common factor, I can say this is y plus z equal to 1. All of these equations give us the same thing. Y plus z is equal to 1, including the first equation we even started with. Equation 1 is y plus z equal to 1. So at this point, I can take any two of these and combine them together, and we're going to see something special here. So let's say I take equation 1 and I combine it with this one here from equation 2. That's going to be y plus z equal to 1, and I'm going to subtract away this equation that we got here, y plus z equal to 1. When I do that, y minus y is 0, z minus z is 0, and 1 minus 1 is 0. We didn't get a solution for either z or y there. We didn't get z equal to a number or y equal to a number as we may have in other examples. But we got a constant number, 0, equal to the same thing. When you get something like that, you don't have an inconsistent solution like the last case. What we have here is a situation where we have an infinite set of solutions. Here, the solution set is infinite. But when we get a statement here that is always true, that means that there is an infinite line for which these planes intersect, for which x, y, and z are all true. So that means that there are a lot of solutions here, to the point that we cannot write this as a single ordered triple. So I'm just going to leave it like that and say my solution there is infinite. There will be ways of writing a ordered triple that would represent an infinite solution, but we're just going to leave that here for now. With that said, I hope that helped you explore some more examples concerning systems of linear equations with 3 variables. Have a nice day.